continue with the problems, and the next problem that we will consider concerning heat and work is problem 2.3. Let us read out the problem as it is there displayed. 2 kilograms of water is contained in a piston cylinder as shown in the figure. This kind of problem we have encountered previously, but the difference here is that this has a linear spring along with the piston. So, you can see that there is a linear spring with a piston and the outside atmosphere. So, the piston is balanced with the aid of a linear spring and an outside atmosphere with atmospheric pressure P1 is equal to P0 is equal to 100 kilopascal. Initially the spring force is 0, so that the external loading is P1 is equal to P0 is equal to 100 kilopascal with a volume of 0.2 meter cube. If the piston just hit the stops, the volume is 0.8 meter cube and T equal to 600 degree centigrade. So, this is again a hypothetical state. It is not the case that it is given that the piston hits the stops. What is given is that had it hit the stops, then the volume would have been 0.8 meter cube and temperature is 600 degree centigrade. Heat is now added until the pressure reaches 1.2 megapascal. This is the actual state 2. You have to find out the final temperature, show the PV diagram and final work done during the process. So, let us draw a schematic of this problem. So, to understand how the pressure within the water is varying, let us draw the free body diagram of the piston, considering that this is our system which is the water. Let us draw the free body diagram of the piston. So, you have the atmospheric pressure, the piston must be having its own weight. No, it is given it is a massless piston. For this particular problem, let us draw the free body diagram with mg, but here this is massless means, see, practically nothing can be massless. In this case, massless means that the contribution of this weight of the piston in terms of the total forces is negligible as compared to the contribution due to the pressure, that essentially boils down to massless. So, then how it is moving? Heat is added. if heat is added, the piston will have a tendency to go up. So, if the piston has a tendency to go up, the spring will try to restore it downwards. So, you have a spring force which is Kx, and this force is Kx because it is a linear spring. Had it been a non-linear spring, it would have been related to x in a non-linear manner. And then you have a force which is P into A, where P is the pressure from the water side. So, this piston is moving in a quasi equilibrium process, that means all forces are balanced. So, you have P into A is equal to mg, which is 0 in this case, plus P0 A plus Kx. So, P is P0 plus Kx by A. So, at state 1 x is 0, that means the spring is completely relaxed, and that is why at state 1 you have P1 equal to P0, which is given. So, this is possible only if the spring is just relaxed at state 1. So, let us try to draw the PV diagram for this process. State 1, so P1 is 100 kilopascal, and V1 is 0.1, meter cube per kg. Okay. So, this is what is given. So, how do you know that V1 is 0.1 meter cube per kg? Actually, you are given V1 total volume is 0.2 meter cube and mass is 2 kg. This is what is given. So, combining these two things are there. Remember, we are doing with water. So, state point has to be identified from the water property table and not from ideal gas relationship. Okay. So, state 1 is identified. Then if the piston just hits the stops, the hypothetical state, then the volume is 0.8 meter cube and T is 600 degree centigrade. So, state 2 and T2 is 600 degree centigrade. So, as we have told many times, but I have no problems in iterating it, because it is a simple compressible pure substance, you require two independent intensive properties to specify the state. So, using these two properties you can identify what is P2 from water table. So, you have state 1, but this is state 2 hypothetical, right. Remember, this is not the actual state 2, this had it hit the just hit the stops. So, this is hypothetical state 2. So, P2 hypothetical. So, 2 hypothetical you get P2 and you get V2. So, 2 hypothetical, 2 hype is somewhere here. So, why this is given? It is given because pressure versus volume is, so how is pressure related to volume? P is equal to P0 plus K into V by A square, because x is V by A. Yes. So, this x is also x minus x naught, right, that x naught is 0. So, this is delta V, you can say, the change in volume, right. So, your reference volume is 0. So, you can of course write it as x minus x naught and this as V minus V naught. I mean it depends on what reference you choose, the reference is arbitrary. So, the important thing is pressure is linearly related to the volume. Okay. So, because pressure is linearly related to the volume, your PV diagram will correspond to the straight line that connects these 2 points, right. So, this hypothetical data point actually helps you to construct the PV diagram without knowing what is the spring constant. In this problem, because the spring constant is not given, you are not able to get a pressure versus volume until and unless 2 data points are given, and because 2 data points are given, a unique straight line can be drawn using this. But remember, this is a hypothetical state point. Your actual state point is when pressure is 1.2 MPa. So, pressure is 1.2 MPa. Now, heat is added until the pressure is 1.2 MPa. Now, whether this hypothetical point becomes a real point, what is this pressure, let me see, this is 1 MPa. So, this pressure is 1 MPa from the table. Now, you tell, is it hypothetical or real? The state 2, see, it started with 100 kilopascal. If it is moving, the pressure is also increasing. The final pressure is given 1.2 megapascal and it is not greater than 1.2 megapascal, it is less than 1.2 megapascal. So, this hypothetical becomes real. Had this been greater than 1.2 megapascal, then that would have been hypothetical, but it is less than 1.2 megapascal, which is the final pressure given. So, this hypothetical we drop now, this we cut, it is a real state point, and then, so at state 2 it hits the stops physically. After hitting the stops physically, what is happening? At constant volume, its pressure is increasing. Okay. So, at state 3 the pressure is 1.2 megapascal. So, let us just write the pressures, this is 1.2 MPa. This is 1 MPa and this is 100 kPa. Okay. So, I mean, before I complete the solution, I mean here just to make it consistent with this x minus x 0, here also we write x minus x 0. Okay. So, just for completeness. Anyway, let us come back to this diagram. So, what is this V2? This is 0.8 meter cube, V1 is 0.2 meter cube. So, you can see all the data points you have on this. So, what is the work done? W13, right, from 1 to 3. So, from 1 to 2 what is the work done? That is, from this diagram is area under this trapezium. So, this is half into P1 plus P2 into V2 minus V1, and this part, because the volume is constant, the work done is 0. So, you can see that by plotting the data and drawing a PV diagram, how easy it becomes to calculate the work done. So, in this case the work done is 330 kilojoule. Also there is another part of the problem, that what is the temperature at state 3. So, how do you find out the temperature at state 3? So, state 3 you have the following properties. What are the properties? P3 is 1.2 MPa and V3 is equal to V2 is equal to 0.4 meter cube per kg. So, using these two independent data, you can from table, water property table, you can find out what is T3. The answer to this problem is T3 is 770 degrees centigrade. Okay. Okay. So, we will work out another problem. Let us erase this. So, the next problem is displayed in the screen. A piston cylinder with a figure below is having the area of cross section of the cylinder as 0.01 meter square and mass of the piston 101 kg. It contains 1 kg of water at 20 degrees centigrade with a volume of 0.1 meter cube. Initially the piston rests on some stops with the top surface open to atmosphere with P naught. To what temperature should the water be heated to lift the piston? If it is heated to saturated vapor, find the final temperature, volume and work done. So, let us try to solve this problem. So, here it is given, let us write the given data. Area of cross section of the cylinder as 0.01 meter square, then mass of the piston is 101 kg, and then water at state 1, what is given? This is the system. state 1 is given by V1 is 0.1 meter cube per kg and T1 is 20 degree centigrade. State 2 is saturated vapor, that means quality equal to 1 and then at state 2 if it is moving, P2 is equal to the equilibrium pressure if it is moving. It means the piston. So, we have to figure out that whether it is actually moving at state 2 or not. If it is moving, its pressure is same as the equilibrium pressure. So, how do you calculate the equilibrium pressure? You draw the free body diagram of the piston. This is P equilibrium into A cylinder mg okay. So, P equilibrium into A cylinder plus right. So, P equilibrium is equal to P0 plus mg by A. This P0 is 1 atmosphere, take 101 kilopascal for example. MP is given G 9.81 and A cylinder is 0.01 meter square. So, if you calculate this, P equilibrium will come out to be 200.4 kilopascal. Okay. Now, question is what was P1? So, that you can get from the table. So, from table you have P1. So, I do not have the data with me, but you will get P1 from water table. Once you get this data for this particular problem, you will find that P1 is less than P equilibrium. So, that you will get once you put this numerical value, you can check, it will be like this. So, if P1 is less than P equilibrium, then what is happening? What is happening is that, see, the inside pressure is less than the equilibrium pressure. So, outside pressure plus weight, it is dominating and it is trying to bring the piston down. It cannot bring it down because the stops are preventing it from doing that. So, then the next is it is heated. So, once it is heated, the pressure will go up and pressure will first reach the equilibrium pressure. So, if you draw the PV diagram, from state 1 it will come to 2A, where this will be equilibrium pressure, then only this will start moving. So, the piston will not start moving until and unless the pressure here is equal to equilibrium pressure. Initially pressure here is less than equilibrium pressure. So, heat is supplied to pressurize this water, until and unless its pressure becomes the equilibrium pressure, it does not start moving. So, its pressure becomes equilibrium pressure and then it starts moving. So, it comes to state 2. So, what is V2? For example, state 2 quality is 1, that means V2 is Vg at P equilibrium. Okay. So, you can identify the state point 2 from V2 and P2. So, P2 comma V2 will give you what is state 2. And then the work done is same as the previous example. So, W12 so 1 to 2 the work done is 0, 2A to 2 is P equilibrium into V2 minus V2A. So, which is same as P equilibrium into V2 minus V1. So, if you substitute these values will give you (157.45 kilojoule). In this case the problem data is very comfortable because the mass is given as 1 kg. So, the mass of water is 1 kg. So, specific volume and total volume numerically they are the same. So,
there is another aspect to one more question, like to what temperature the water should be heated to first lift the piston?
To what temperature the water should be heated to lift the piston. So, that will be the temperature corresponding to state 2A. So, this is another part of aspect of this question, that what should be the temperature at state 2A. So, state 2A, how do you identify state 2A? Two properties you have to search. One is P2A is equal to P equilibrium and V2A is same as V1. So, these two will give you the state point 2A, and from table you can, from water table you will get what is T2A. So, the answer is 120.2 degrees centigrade.
Basically the answer for both the parts is the same because that line 2A to 2 is inside the saturation zone. So, that is a line of constant.
Yes, from 2A to 2 this straight line has to be in the saturation region, because this was in the saturation region, this is in the saturation region and this is quality equal to 1. So, this cannot cross the saturation region and go to superheated region. It is, this is in the saturation region or two phase region. So, from two phase region it is going towards superheated, but it does not cross superheated because at state 2 it is quality equal to 1. So, because it is, this is the same saturation line. So, the temperature here and temperature here both are actually saturation temperature corresponding to P equilibrium, which is to 120.2 degrees centigrade. Okay, let us stop here today. We will continue with other problems in the next lecture.